Hello everyone, and welcome to the simulation team's first tutorial video for fall 2016. In this video we will be solving a modified problem from my Deformable Body Mechanics textbook with an ANSYS static structural simulation. To help learn the program, I suggest you watch this video on a CSE Labs computer if possible, and follow along for your own. You can learn even more by modifying the simulation after you're done and experimenting with all the other things you can do. One more logistical thing, I'm recording this on a 4K monitor and some of the text might be a little small, so I'll re-record the video with bigger text if that becomes a problem. With that in mind, let's get started with our first example question. We are asked to find the reaction forces on each ends of bar AB due to the uneven heating of the bar. The temperature distribution is given in the problem, and the dimensions of the cylinder are also given. This is everything we need to set up a simulation and give an answer. The steps we want to go through will be shown once we start the ANSYS program and specify our type of simulation. ANSYS is installed on all CSE Labs computers. It's easiest to launch by going to the search box in Windows 10 and typing in Workbench. 17.1 is the most current version, although the user interface doesn't change a lot with each new version. While the program launches, let's go over the problem some more. Heating the bar, especially unevenly, causes it to expand, but the rigid supports provide no room for expansion. As a result, the bar exerts a force on the supports, which exert an equal and opposite force on the bar because of Newton's third law. When ANSYS starts, you'll see a big blank window with a toolbox on the left-hand side. Here's the toolbox, and it has all the projects that you can choose from. We want static structural, which you need to click and drag into the rectangle that appears in the workspace. The box that appears has all the steps in the simulation. I'll quickly run through them before getting started. We'll create the virtual steel bar in geometry and add the proper dimensions. The material is already specified in engineering data. It defaults to structural steel automatically, which is the material of the bar. Next is model. We'll mesh the bar in this section, more on that later. Setup is where we'll apply the temperature to the bar and fix the ends. We can also select the solution from that window, solve, and interpret the results. Model, setup, and solution are separate steps, but we deal with them in the same window. We'll start by creating the geometry, which is done by double-clicking the Geometry section to launch Design Modeler. Design Modeler is the CAD program within ANSYS that we use to edit geometry. When it's open, you'll see a big blue window and a tab with 3 planes, XY, ZX, and YZ. Those are the base planes for our standard XYZ coordinate system. Alright, to get started with the cylindrical bar, we need a cross-section to extend into a cylinder. We can do this by drawing a circle on one of the planes using the Sketch tool. To do this, select one of the planes by clicking on it, and then click the New Sketch button on the toolbar. Select the Sketching tab, and then select the circle. To draw it, click once on the origin, and then click again somewhere else. Now that we've got a circle, we need it to be 0.1 meters in diameter. We do that using the Dimension tab, then select Diameter, then click on the circle. Click anywhere to set the dimension. Go over to the Details section on the lower left side of the screen and select the box next to D1. Type in 0.1, then hit Enter. ANSYS defaults to SI units, so you don't need to specify meters. But if you need different units, click the Units menu, then select your preferred unit of length. Quick tip, whenever you add a feature to the simulation, the details will need to be specified in the Details section in the left side of the window. Now we need to extrude the sketch into a 3D object. But before we do that, let's take a better look at our circle. Press the Zoom to Fit button or press F7. Select the Pan tool, drag it to the center of the screen, and then use the mouse wheel to zoom in some more. Go back to the Modeling tab, Select Sketch 1 and then click Extrude. Click Apply for the geometry. We already specified the geometry when we selected the sketch before clicking Extrude. If you have multiple sketches and you didn't select one before clicking Extrude, you'll need to select the sketch in the geometry field. Type in 1 meter to the depth field, then hit Enter. Once the extrusion is ready to be made, the extrude feature we are working on gets highlighted with a lightning bolt. This means it's ready to be generated. Select it, then press F5 to generate, or click the Generate button. I'll zoom out so we can get a better view. And I'll pan over. So once that's done, we have our bar, and now we're done with the geometry. You do not need to save your work. The project takes care of that by itself. Just click Close, and we'll proceed to the next step, the mesh. Double-click Model to open it, and a window will pop up in a bit with our new geometry. The next step is to mesh the geometry. I might go over mesh a little more in subsequent videos, but for now I'll just say that the meshing process splits up the bar into small elements, each of which the program generates equations for and solves during the solution process to give the final results. The mesher does a pretty decent job of generating the mesh automatically. It'll do so if we right-click Mesh and select Generate Mesh. This might take a while depending on the computer and the number of cells in your mesh, but after a few seconds the bar should be split up into a bunch of cubic cells. You don't need to count them, just expand statistics, which is found right there, after having selected mesh, and you'll see the number of elements. We can reduce the size of those elements to get a more accurate simulation, and in doing so we'll create more elements to fill up the entire geometry. To do so, right-click Mesh, hover over Insert, and select Sizing. Select Body for the type of sizing, click on the bar, and then select the geometry field and click Apply. Then go to the element size window and type in 0.025 for the element sizing. Hit Enter and regenerate the mesh. Doing so should give you some more cells, and we'll get a more accurate simulation. That's it for the mesh. I might cover some more mesh sizing in later videos. Let's move on to specifying the problem conditions. But before we do that, let's take a look at the problem again. The bar is held up by two rigid supports, which we need to apply to the ends of the bar in our simulation. Go back to the program. To insert those supports, we need to right-click Static Structural and hover over Insert. You'll see a menu where you can insert forces, pressures, supports, and a lot of other things. Click Fix Support, and then click either end of the beam. Then click Apply down below. We need to repeat this for the other end of the beam since both ends are fixed. You may need to rotate the beam to get to the other end. Now for our problem, we need to consider what we're doing to the beam. We're heating it up with a temperature distribution given here. The temperature as a function of x is equal to the temperature at end B times x cubed over the length cubed. In our case, L is 1. And the temperature TB is 20 degrees Celsius. To insert that temperature, we once again need to right-click Static Structural, hover over Insert, and then click Thermal Condition. To fully specify the temperature gradient, we first need to specify the geometry by clicking on the bar, and then click Apply. The bar should turn red. The temperature isn't uniform, however, so you can't just specify one temperature. Click the right arrow in the magnitude field. Notice how constant is checked. We want a function instead of a constant, so select function. Go to the magnitude box, and then type in the temperature as a function of the variable along the length of the bar. You may need to rotate and look at the coordinate system to see what that variable is. In my case, it's z. So I'm going to type in 20 asterisk for multiplication, lowercase z, caret for exponents, and then 3. Hit enter. Take a moment to look at the bar now. Notice that the temperature is high at one end and low at the other end, with the distribution given by the graph. It's cubic, so that's what we want. One last thing to do before solving, we need to tell the program where we want to find the solution. Sorry, what we want to find in the solution. The problem asks for reaction forces at both ends of the beam. So right-click Solution, hover over Insert, and then hover over Probe. Now select Force Reaction, then click the field next to Boundary Condition in Details. Select Fixed Support. You'll need to repeat for the other side, but select Fixed Support 2 this time around. After that's done, here's an optional step. If you want some cool visuals to look at, right-click Solution, go to Insert, go to Stress, then click Equivalent von Mises. Do the same, but under Strain this time, for equivalent strain. Now that all that's done, it's time to run the simulation and solve for our desired results. Select Static Structural, then hit F5, or right-click Static Structural, and click Solve. Wait for the program to solve. This progress bar will show you how close it is to doing that. So while we wait, let me tell you a little bit about what's happening in the coming weeks. If all goes well, I'll get the forces and displacements next week with some more complicated geometry, so you can gain more of an appreciation for how simulations can help solve complex problems. The week after that, I'll do a SolidWorks demo and another statics problem. After that, I'll probably start on fluid flow simulations and how they apply to rockets. After your simulation is finished, each result should have a green check mark next to it. Select the force reaction results and check in the details section of the lower left corner. You should see the X, Y, and Z components of each force. The direction along your bar, in my case Z, should have a large value compared to the other two axes if setup and geometry are correct. Notice that the reaction forces are equal and opposite. That's because of Newton's second and third laws. Specifically, the bar can't move, and the reactions of the supports on the bar are equal and opposite to the forces that the bar exerts on the supports. Now, upon selecting the stress or strain results, you should see the bar highlighted in different colors corresponding to a scale of stress or strain. Now, you should notice how this bar looks a little deformed. That's putting it mildly. But that's just because of the scale. You can select 1.0 for true scale. That's what the bar would actually look like were we to run this in real life. Well, you can't really run in the real life. Well, run the experiment, I guess. Anyway, stress is the amount of force per unit area, and that's what happens when a force is applied to a surface. Here it's the ends of the bar that the forces are being applied to. Now, strain is a change in length of a material divided by its original length. It measures how far 1 meter of bar stretches, in meters, for every meter of unstretched bar. If you want to know more, look up engineering stress and engineering strain on Wikipedia. So we have our answers for both reactions. In my case, it's 3.2654 times 10 to the 5th newtons, about 326,000 newtons. Those are units of force, so we've done our job. That's it for the video. More tutorials will be uploaded to this channel while I prepare more example problems. We'll get to rockets hopefully by the 7th week of the semester, which is about 3 weeks from now. Feel free to play around with any of the setup conditions and see what happens to equivalent stress, strain, and reaction forces. Thanks for watching, you guys, and I'll see you next time.